We have a simple example here to illustrate how we can use a line integral. So this differs from physics 1, where we only move things in one direction, straight line. Now we're going to move it in straight lines, but in different directions. So we're going to start with this is being a tabletop, and this little dot we have here is your textbook. So we're going to make a little reference frame saying this is our X and Y frame. This is position x equals 0 and y equals 0. So in principle, we could take our reference frame and we could put it to coincide with that point. We're going to move it to a new point that's given by 0.3 meters in x and 0.2 meters in y. And we're going to take a path such that we move it along x first, and then we move it along y. So we split it into two segments. All right. So let's see how we can use the line integral that we just talked about in the previous video. So the textbook has a mass of 2.18 kilograms. I actually put it on a scale to figure it out. And we're going to assume we're applying a constant force of 5 newtons. So first we're pushing 5 newtons along the x direction, and then we push 5 newtons in the y direction. So how much work is done by pushing it? So the work is defined as the line integral along some line or curve of the applied force dotted with the infinitesimal displacement along that curve, and then we're summing them up, and that becomes the integral. As we showed earlier, we can write the dot product out in terms of the scalar components. We can use the geometric approach where we get force and cosine the angle. The angle is a little bit tricky because it's changing along this path. So we'll use the component form. This is two-dimensional. There's no c components here. So we have a contribution due to our x components. And we're going from x1 to x2. This is along the first path. So we can break this into two paths. Let's call this here along path 1. And this is path 2. So this integral here represents the work along path 1. Then we add the work done along path 2. But that is the principle, just the y component we have here, because there's y not x. Okay. Going from y1 to y2. That is the configuration of this path. So this here represents the work done along path 2. So let's see what we can do with that. Now we're starting at x1 is our starting x coordinate. That is 0. We're ending up at this point here for path 1, or segment 1. That is x equals 0.3. The x component of the force, well, it's a constant force. What are we moving along x, along y? So along the first segment, the force is along the x direction with a magnitude of 5. This is not the magnitude, it's the component, and that's important to stress out. It's the component, so it could in principle be negative, it's not the magnitude. In this case, our component is positive 5 because we're pushing in the positive x direction. So that is 5. Then we are having the x that we integrate respect to. The second term is when we go along path 2. So we're starting at y equals 0. We move to y equals 0.2. So that's our final point here. In this case, we're pushing along the y direction with a magnitude of 5. So we can insert the magnitude, so not the magnitude, the component of the force, that's a positive 5. Integrate with respect to y. Now we can carry out the integrations. See, this is a constant, so we could bring that outside the integration. We can do exactly the same for path 2. Okay. Now we're integrating over x. In principle, we can read this as being a 1 in front here. So the integration, the definite integral with respect to x going from 0 to 0.3, skipping some steps here, is simply 0.3 plus similar argument here, integrating from 0 to 0.2 over our displacement. That's just going to be the exact displacement here. Going from 0 to 0.2 is just 0.2. And we can then multiply it out. This is 1.5 plus 1.0. So the total work done is going to be 2.5. The units are joules. So the total work done by applying a force of 5 newtons along this path is 2.5 joules.